All good. All right. Hey, everybody. We are back. I'm going to adjust my screen just a little bit. Hey, welcome back to the second lesson of the second model in our 2024 STEMNetX Data Science Workshop, Boot Camp, whatever we're calling this thing. Up to this point in the workshop, we've been covering a lot of skills that are kind of core, maybe programming skills, analysis skills. We're now going to start to talk about applications of those things. So what we're going to talk about in this lesson is absolutely vital in the modern sciences. It's the idea of data visualization. Before we talk about why we visualize data, maybe I just want to give you a good example. And this is a very timely example, especially for young people today. I want to just click through to the New York Times coronavirus in the US tracking pages. Now, as of March 2024, these pages are no longer being updated, but for a long time, these are data visualizations that I looked at multiple times per day, certainly in the spring of 2020. It was information like this that were just kind of dominating our lives. There are many, many really hard-hitting data visualizations on this page. And perhaps this is a good time, or with this kind of map up here, is a good time to talk about what a data visualization is. When we talk about data visualization, we are talking about a process by which we take quantitative information and then display it in a form that is much more easily digestible to a human brain or human eyeballs connected to a human brain, or not just easier to digest, but that tell a more salient or more obvious story. So show trends in data more obviously, or show correlations between different quantities, different variables in some type of analysis. So a good example maybe, and we'll get into this in a minute, is if you think back to a previous lesson, we had that one data file that contained data on the rolls of dice at a craps table in a casino. It's very difficult to open that file up in a text, some kind of text program, text viewer, text editor, and just kind of scroll up and down through the file. Where's my finger in the camera? Scroll up and down through the file and read the individual numbers and get a sense of, okay, how are these rolls actually distributed? What's the mean? What's the max? There's just too much information there for our squishy human brains to process all at once. However, a visualization or a graph of that data might help us form an understanding or a better understanding of that data as a whole in just a single glance. And that's what we're going to be working on today. So these coronavirus tracking pages, or this page is no longer being updated. It's kind of like a walk down memory lane to look at some of these graphs. Time series data like this is extremely, extremely kind of visceral. You can remember back to some of these times when the hospitalizations were just very, very high. Ooh, there's a lot of stuff there. Okay, so let's close that for the time being because I'm being triggered. All right, so I kind of said this already. Data visualization as an idea. By that, we just mean by data visualization, we mean, is there a way to represent visually some collection of information in a way that helps a viewer understand this data better? And in many cases, that can be a result in a scientific analysis. To find a relationship between two variables, a bivariate graph is a good way to do that. So this is an incredibly powerful tool. I talked a little bit before about how Python is an open source project. There are many wonderful libraries that community members or community Python developers make. The library that we're going to be working with today and for all of our visualizations in the future is just an amazing example of an open source community-led project. It's a library called matplotlib, or matplotlib probably is the correct way to say that, but I think most people say matplotlib. This is a library that gives tons and tons of plotting and graphing capabilities. We're going to just take a look at the absolute tip top of the iceberg here for some of the standard ways that we visualize data. There is so much more that we're not going to talk about today in matplotlib. I would encourage you to just kind of Google around or watch a video. There are two great resources here linked in the notebook file. So the first is the homepage of matplotlib, matplotlib.org. And then there's always the really great Python graph gallery, which gives examples of many different types of graphs, but then also talked about, okay, what are the most common use cases? When would you use a certain type of graph? What would you be trying to learn about data? And what type of graph would help you learn that thing? We're going to start very simple and we'll work up to more complicated things as I usually try to do. All right, the first data visualization that we're going to talk about is a histogram. A histogram is a way of showing a distribution of one-dimensional data. So if you think about some type of data set, the one that I usually think of, and we'll get into this in a later lesson on fitting data, I think about, hey, you have a large collection of people, you measure all of their heights. That's a one-dimensional data set. It contains only height values. Is there a way that we could visualize that data that would help us to understand the general properties of that population of people? And the answer is yes. The easiest way to do that is with a histogram. Now, you may have interacted with histograms a lot in the past. I'm sure you've seen histograms. Often histograms are referred to in kind of popular speak as bar graphs. They are not technically the same as bar graphs. I'll show you why there's a difference between those two things in a minute. Basically what a histogram is you can, think of a bar graph, fine. On the horizontal axis, you have the range of values that where are my fingers? You have the range of values that your one-dimensional data fills, or along the range in which that one-dimensional data falls. And then the vertical axis basically displays how many occurrences you have in each little sub-range of your one dimension of data. It's kind of tough to describe in words. Let's make a histogram and I'll show you. All right, so you can read through this backstory here. There's a lot of really, really well-written and insightful commentary there on histograms. What we want to do right now is let's go back to the DICE data set that we worked with in the last lesson or previous lesson, and see if we can make a histogram, a visualization of the total of the rolls of the two dice. So recall that this DICE data set contains each row as a different occurrence of someone rolling the dice in a craps game. There are two dice. Each row contains the roll number, so basically just the row number. Then it has which way do I want to go here? It has the row number, it has the value that the first die took, it has the value that the second die took, and then it has the name of the croupier, the name of the person who was in charge of the table at that time. So what we want to do is we want to open this file, we want to read through it line by line, we want to add up the values of the two dies, and then we want to make a visualization of that. So the first chunk of code here, we just have two library imports. We've seen NumPy before. We're going to need NumPy in a more meaningful way in order to do our data visualizations. The second import line, we're just importing from the matplotlib library this module called pyplot, and we're giving it a shorthand, just PLT. Pyplot you can think of as kind of the core functionality from the matplotlib library. Then here's a line that we've seen in the past. I'm opening the DICE data file. Make sure you've downloaded that and uploaded it to the Jupyter Notebook browser. I'm then initializing an empty list, which I'll call total rolls. I'm just going to store the total of the two dice for each roll in this list. And then what I do is I read off that header line from the file. I read the first line of actual data from the file. Why can't I triple click that line? There we go. And then I have my typical while loop. So this while loop is basically just going to continue happening while I'm able to read off a line from the file that has some information in it. I split the line from the file everywhere where there's a comma. I do that because this is a CSV file, a comma separated value file. I add up the values that are the index equals 1 element of that list and the index equals 2 element of that list. When Python reads those values in, when it reads in the line from the file, it treats everything in that line as a string. So I also have to cast those values as integers. So I'm adding up these two ints. Then I just append that total value to that total rolls list that I talked about before. And then I grab the next line from the file, and then the whole loop happens again. I then close the file. No big deal there. No reason to leave it open if I'm done with it. Then this is a new piece of code for us. So here we're basically taking the total rolls list, and it's almost like a cast. We're turning it into a different type of object. The different type of object is a NumPy, numerical Python. Remember I imported NumPy as NP. It's turning it into this thing called a NumPy array. For all of our intents and purposes, you can think of a NumPy array as just like a list, a Python list on steroids. It has a few additional properties, probably many additional properties, but we actually want this data to be in a NumPy array form, in a data type, a container of a NumPy array. so that it can be plotted by our plotting code below. All right, then we get into the actual meat of the stuff that we're learning today. So we want to visualize this data. How do I do that? It's as simple as I want to make a histogram. I call PLT, that's the pyplot module, .hist. Hist is an actual function that lives in this pyplot module. I have to provide hist with a bunch of arguments. The first is just the Python NumPy array that contains our data, total_r for total array. I then have to tell pyplot what I want the range of values. So on the horizontal axis, which way are my fingers going? I'm kind of backwards today. What should the range of values that I want to display on the horizontal axis to be? Here I'm telling it make the minimum, which way do I want to do this? Make the minimum 0 and the maximum 13. The next is how many bins do I want to chop that range up into. So I'm going to get a series of rectangles here that show the number of dice rolls I have in each range. I want this to be 13 bins. So effectively I'm chopping a range from 0 to 13 up into 13 bins. Each one of those bins is going to be 1 unit wide, and there will be 13 of them. And then this is some formatting stuff. The histogram type that I want to display is a step type. You'll see what that means in a moment. I do some formatting stuff. So this line allows me to give the x-axis a label. This line allows me to give the y-axis a label. This line allows me to give the plot a title. Give a title of the graph. You can already see it peeking out down here because I already ran this code cell. Sorry, that was anticlimactic. And then the last line in this file, or in this code cell, maybe isn't strictly necessary because of the way a Jupyter Notebook works. But plt.show just tells Python, hey, we definitely want to see this graph right now. We're not just making it so that we can save it to file. That's something that we could do later. We want to actually display this thing on the screen. All right, so let's run this code cell and check out what we get. So all of that code, I mean, there's probably, let's be very generous and say that there's 20 lines of code here. That's probably close to spot on, is all it took to make a nice graph. Now, it's certainly not the most beautiful graph in the world. We're using very, very basic formatting options here, but this thing happened very quickly and on the fly. I didn't have to remember where the menu is that will allow me to set the title of the axis. I didn't have to do a whole bunch of clicking and dragging to highlight my data. I have a ton of control over what I am actually graphing here, and it came out to be exactly the thing that I wanted. So the functionality or the syntax here, we will see the same type of syntax over and over and over again. It turns out histogram is just one type among many of data visualizations that matplotlib is capable of and actually very good at. If I wanted to make a scatter plot, a two-dimensional graph, a 2D histogram, the syntax that I would use here is actually very similar. So the wrapping your head around this syntax now will be handy later. Okay, so you can see this thing kind of looks like a bar graph. Just to be very, very clear, what you're looking at here is the height of each one of these rectangles, and I plotted this thing as a step type histogram, which means that the next door neighbor rectangles just kind of join to one another like steps, like stairs in a staircase. But the height of each one of these rectangles tells me that when 2 dice were rolled, the total of those dice was equal to 2, so this bin right here is like total equals 2, and it looks like that happened about 300 times. The total was equal to 3, so this bin right here, that happened about 600 times. The total was equal to 4 about, 850 times. What was the most common occurrence of the total? Well, it looks like it was 7. So the highest point in my histogram is this bin right here. That's the bin that corresponds with 7. And that happened about 1,650 times. I think that's what we found in our previous lesson when we actually analyzed the data and calculated basically the number of times that 7 came up. And you can see that once the total gets above 7, that happens less and less frequently. That's exactly what we expect from 2 die. Now, one of the questions that we'll work on later is whether there's some funny business going on here. So are both of these die, what's the word for it, fair die? Is there an equal probability of any side, any of the 6 sides of the die coming up in a roll? One way that we can begin to investigate this now is to do a warm-up problem. So now we're going to change the code above to plot the individual rolls of die 1 and then die 2. We're going to see if we can plot these two histograms on the same set of axes. Is something funky going on here? All right, so let's do this. I am going to, a great way to adapt a problem is to just steal all of the code from a previous code cell. So what I'm going to do, I don't need to re-import the NumPy or matplotlib libraries. I'm just going to steal all of the the actual code that does something in that cell, and I'm going to paste it down here. Okay, so I'm still going to open the same in file. I'm not going to tabulate the total of the rolls of the two die. What I'm going to do is do like die 1. I'm going to have a separate list for each one of those die. So I want to initialize two different lists like this. And now might be a good time to show you a really cute way that I can initialize multiple variables. I can do it all on one line by just saying die 1, comma die 2 is equal to empty list, comma empty list. So I can kind of set an unlimited number of variables. I can initialize them on a single line like this. All right, I still read the first line off of the file, that's the header line. Then I read the second line off of the file, that's the first data line, and then I just start doing stuff. So I don't really need this total variable. What I need to do is I need to just start appending information to my two lists. So I'll say die1.append. What I want to append is an integer cast of line array element 1, because I've already splitted my string line into an array like this. And then basically I want to do the same thing for die 2. Okay, looking good, but I want to go with the second element. And I can get rid of this line because I'm not tabulating the totals yet. And then I want to read the next line off of the file. So that's looking good. So look how quickly, look how easily I changed what this, this block of code was doing. Again, this block of code is just responsible for reading the data in. I'm then going to close the file. This line looks good. Then what I have to do is I have to convert those die 1 and die 2 lists into die 1 and die 2 arrays. So I'll do die 1 array is equal to np.array of the die 1 list. And then of course I can just copy this line like this. All right, we're looking good. So I'm basically doing a second copy of all of the things that happened in the previous code cell. All right, check this out. Did you ever try to graph two sets of data on the same set of axes in Microsoft Excel? Microsoft Excel gives you the impression that it really just doesn't want you to do that. It's incredibly, I don't know, difficult for me at least. I'm not an Excel power user. Here's how we would do this in matplotlib or with using matplotlib. So I'm going to make a histogram out of the first die's data, and I guess I have to do this with die array, and I'm going to do this with die 2 array. Look at that. I make a histogram of the die 1 data. I give it this range, I give it these bins, and I give it that histogram type. I do the same dang thing with the die 2 array. Let's see if this works. I don't know if this is going to work. I maybe made a mistake somewhere. Holy cow, it did work. Look at that. Now, it made a histogram. The histogram doesn't look as good as the previous one looked. And the reason for that is the data for each of these individual die should, individual dice, or for each of the dice individually. I don't know how to say that. You know what I'm talking about. Is going to fill a different range. So the total could go up to 12, 6 plus 6, but the individual die values can only go up to 6. So let's change this histogram just a little bit. We will make it go, each one go from 0 up to 7, okay, because we don't need that full range up to 6. And I'll change the number of bins to display 7 bins, and we'll rerun this. Okay, check this out. There's a hint of something funky going on here. If these are fair dice, you would expect that the number of times that each die came up with each one of the faces, each one of the numbers, would be totally equal. There would be some statistical variation, but it's looking like these two histograms are not alike. It's looking like die 1, which I think is the blue histogram, it's a little less likely for it to roll a 3 and a lot more likely for it to roll a 4. Die number 2, which is the orange histogram, is a little bit more likely to roll a 3 and a lot less likely to roll a 4. You know what, we can even add a legend to this graph pretty quickly. Let me see if I can do that on the fly. So I'm going to do that. I need to specify a label for each one of these histograms. Label. So this label option is what these data are going to be referred to in the legend on the histogram, and then I'll do plot.legend like this, and that's all I need to do to make a legend on this graph. Check that out. That was really quick. You do not want to see me try to make a legend in a graph in Microsoft Excel, because there would be a lot of swearing probably. All right, so this is really nice. And one of the other nice things about this I've mentioned before, if we get a new data file that has similar data in it, so like let's say you're the casino owner and you're like there's some funny business going on at my craps tables. So you have somebody collect more data. All you have to do to run this same graphing code on that data is change the name of the data file, and all of this code will work the same as long as the data file has the same formatting. So these tools are incredibly powerful. They're very flexible. You know, there you have it. Okay, so let's talk about bar graphs really quickly. A histogram is a graph that shows, using bars, the distribution of data along a continuous axis, like this down here. A bar graph is like a histogram, but it's something that graphs without a continuous axis. It usually is graphing the number of occurrences of some categorical data. So here is a container type. You might recall that this is a Python dictionary. I almost goofed that up. This is a Python dictionary. The dictionary has keys. The keys are names of dishes that you might order when you go out to eat. And then it has a number associated with each one of those dishes. I can turn this into a bar graph by making an a list out of the keys in this dictionary, a list out of the values in this dictionary, and then by calling pyplot, plt, .bar. Bar is the function for a bar graph in pyplot. I provide it with the list that is a list of keys and the list that is a list of values, and it makes one of these categorical bar graphs here. Now, you can tell right out of the gates that this is a different thing because these bars are not connected to one another. There's no continuity on the horizontal axis. There's no real way in which pad thai and malai kofta are, continuous types of dishes. So these are different categories of things. It's not a continuous, I'm really off in the camera today. It's not a continuous axis. All right, we'll see more of these plotting capabilities as we go on. Again, this is just a very quick demo of how you might make a bar graph. You should also be aware of things called two-dimensional histograms. So the histograms that we made above are one-dimensional histograms because they show the distribution of data along a single dimension. There's a single axis there. Above, it was the total of the rolls of 2 dice. You can also show the number of occurrences of data along 2 axes. And we do that with something, there are a bunch of ways to do that. One way is with a 2D histogram. You can grab this lizards.csv file. It's in the data files directory on GitHub. And I'm just going to make a 2-dimensional histogram of this. The code is very similar. Okay, it's very similar to what we used above. The couple differences are here, we're using a 2D histogram, or a hist 2D, rather than just a hist. And there's some more formatting options that I have to use as a result of that. There's going to be more data. So let me just run this and you'll see what this thing looks like, and then we can talk about it. All right, so here is a 2-dimensional histogram. This is displaying the number of data points, or number of occurrences, that happen along 2 continuous dimensions. So let's say that I've collected 100,000 lizards that I just found in my office, which is Swanson 100B in the Swanson Science Center at W&J. I measure their lengths and I measure their weights. Really, this should be mass because I'm measuring in grams. Forget about it, okay? This isn't Physics 101, so I guess I don't have to yell about that. The way this 2D histogram works is it chunks up each one of these axes into bins, just like we did in a 1D histogram. But because we are dividing this plane, 2-dimensional plane, into bins along this direction and bins along this direction, we wind up with rectangular cells. The color coding in each one of these rectangular cells is shown on the axis at the right. So we have a color spectrum here that goes from white, which would correspond to 0 lizards, up to deep purple, which would be like, what, maybe 320 lizards, something like that. And you can see certain combinations of lizard weight and lizard height are very prevalent. So maybe 10 centimeters and 500 grams is a very common occurrence. Other combinations or other lizard parameters, I don't know what to call it, are much less common. So somewhere out here, I've definitely found at least one lizard that has a mass of 1.7 kilograms or 1750 grams and is 14 centimeters long, but they're very rare. So out of the 100,000 lizards I've found, only, I don't know, single digits number of lizards had that very large mass and pretty long length. 2D histograms are very, very information-dense visualizations. There's a lot going on here. You can see like a relationship, kind of like a general relationship between weight and height. This is actually a very simple data distribution displayed on this 2D histogram. It can take a lot of looking at 2D histograms. Usually they're very difficult to digest the first time you're seeing a 2D histogram, but after making them and using them, they will become more comfortable to you if you wind up having to use them frequently. All right, let's talk about graphing bivariate data. So by bivariate data, this is just a fancy way to say a 2D graph. You have a horizontal axis and you have a vertical axis and you have some data points in the plane there. This is actually pretty straightforward with matplotlib and pyplot. So let's take a look at this data file. This is somewhat of a morose or morbid data file. It contains time series information on the number of deaths in 122 different United States cities between the dates range of 1962 to 2016. It's a pretty big data file. There's a whole bunch of different cities in this data file, and there's a whole bunch of different years. And I think we'll see in a moment that it's the number of deaths per week. So the code that I have here is a little bit tricky, but it's basically the same type of functionality. I'm going to initialize empty lists that are going to store my data. I'm going to specify the city that I want to consider here. You'll see why that's important in a minute. We're going to read in the data using one of these while loops, and we're only going to keep data that's specified for the city that we specified above. So we have an if control statement here that says if the fifth element of the line array is equal to city, now we set city to be Pittsburgh up here, then we're actually going to append this data to our list. There's some other funky stuff that has to happen in here. You can ignore that. I just want to show you the basic functionality. I convert those two lists to NumPy arrays. Great, we've seen that before. I then am going to make a plot. If I want to graph bivariate data, the simplest way to do that is with a pyplot plot. What do I supply as arguments? I supply the week number, which is, you'll see in a minute, is one of the arrays that I'm generating here. DS is the list that stores the number of deaths in that week. And then this last element here, this last argument, is just a formatting argument that basically tells Python, hey, for each one of these data points, make it a wee little like period shaped thing. We can change that in a minute. I'll show you how to do some formatting. The rest of the stuff here is pretty straightforward. So plot.ylim allows us to set the limits on the y-axis. So I'm setting ymin equal to 0. I make the label for the y-axis. I make the label for the x-axis. There's one thing missing here. I should probably close this data file. What am I calling it? fill.close. There we go. Oh, I was doing that below. Oh my goodness, I didn't even see that last line. This was perfectly written code before. I doubted myself. All right, let's run this thing and look at the visualization. All right, there we go. Now, there is a lot of data here. So a year has roughly 50 weeks in it, and this data ranges from, what did I say, 1962 up to 2016. I don't know, that's 50 years, so there's 50 times 50 is 2,500. There's a lot of data points here. Holy cats, that's a lot of data points. But this data visualization is not chaos. So we can see some important takeaways. One is that the number of deaths per week in Pittsburgh is for the most part going down. Number 2, we can kind of ballpark it around, I don't know, between 100 to 200. So that's information that we can grab right off of this graph. Now, those are not exact numbers, but it gives us a ballpark range. We can see that there are some weeks that have significant higher numbers of deaths, and there are some weeks that have significantly lower numbers of deaths. Maybe we can even see some kind of strange clustering or trend over here. There is a lot going on in this visualization. Now, we can't look at this visualization and say, aha, we completely understand the reasons for and ways in which people die in the city of Pittsburgh. We can't know that. However, this visualization is incredibly useful for giving us an idea of, okay, what are the next questions to ask? Why is the number of deaths in Pittsburgh going down? Is it because people are living longer? Is it because fewer people live in Pittsburgh over time? Why is there so much scatter? Were there terrible events that happened on some of these days where there were just many, many deaths that week? Are there other things that we can learn from this data? So, admittedly, it took me maybe 10 minutes to write this code cell that would make this graph. Okay, and I'm not kind of a professional. Okay, fine. But you could totally copy and paste this code and edit it to meet your purposes. The one lesson that I want you to take away from this, the one big takeaway from this lesson is that once you write this code, you can adapt it to so many different problems. So this code right now definitely graphs the deaths per week in Pittsburgh. What if I don't care about Pittsburgh? What if I want to study New York City? So let's just change this to New York. Now, I've done a lot of looking at this data file. I understand how it works. But that was a very quick change, and it gave us a completely different graph. So here we can analyze New York City. The deaths range between 1,000 and 2,000, roughly. New York is much larger than Pittsburgh. The data is a little bit less scattered, at least at the zoomed out level. And we see maybe some interesting trends. So here it was kind of maybe level in 1960 to 1970, then it took a dip and then it leveled off again, maybe even increased. What was happening in the 80s to 90s to give this increase is a very interesting question, public health question. Let's change this one more time. I want to show you one more city that is very interesting. So Charlotte, North Carolina, I think is the city that we want to look at. Charlotte, North Carolina, the number of deaths per week has gone up dramatically by a factor of, maybe 3 in the last 50 years. Now, why is that? Is it because Charlotte has become an insanely dangerous and morbid place to live? Probably not. It's probably because, 50 years ago, Charlotte was in the wilderness, and it's become really quite a large city in the years since. So the population of Charlotte has grown a lot, and therefore the number of deaths has grown a lot too. The number of deaths per capita, per person, per 100,000 people has probably gone down, just like all of the other cities that we've looked at so far. But because the overall population has increased, we see this graph. So these visualizations, now again, you could totally open this data file in a text editor and just look at the actual numbers that are in the data file, but you would not be able to get this kind of high-level understanding of the trend in the data without making a visualization. Data visualizations are super, super important. All right, so there's some more stuff to read in there. I showed you I had some code in a previous lesson that plotted this parab t, x, and y data. Whoops, what happened here? Parab t and y. Oh, I guess I didn't download this thing. Or maybe I didn't upload it. Let me upload this file real quick. Let's go to downloads. It should be under P for parab. I apologize for the hiccup here. Okay, there we go. It's now in my browser. We should be able to plot this. There we go. So that's a bivariate plot. It has data that have a horizontal axis value and a vertical axis value. We see a nice parabola. That's exactly the code, or very similar to the code that I had in the previous lesson. What are some other things that we can do with this? Well, we can also use matplotlib to plot functions, to actually graph not data, but continuous functions. The way that we would do that, or one way to do it, is to define functions. So here I have 2 functions. Function 1 is going to be a hyperbolic tangent function, one of my favorite functions. The function 2 is going to be one of the things that we call a sigmoid function. So it's 1 minus 1 divided by 1 plus e to the power x. So this is some very compact NumPy syntax for calculating e to the x and hyperbolic tangent of x. And we're going to take a look at the difference between these two functions. The way we do that is we make lists, or a list of x values, and then we just operate on that list of x values with each of these functions to create a set of y values, or a list of y values. Then we just graph y versus x. So we're going to make two plots down here. This while loop basically just does that applying of the function to each one of the, or to different x values. We convert those lists into NumPy arrays, and then we do our plotting down here. So you can see the pyplot.plot calls. The first one plots the x array on the horizontal axis and the function 1 array on the vertical axis. The second one does the same thing, but with function 2 instead of function 1. I provided some labels for our legend and some other stuff here. It's interesting, one thing to point out is the formatting for the points is different. So here I've said, hey, instead of using a period to display each one of the points, when I put a hyphen there as the formatting option, it's going to connect all the points with a line, hyphen like a line. Okay, let's take a look at these visualizations. There we go. So I've got two different functions, and the way that I've plotted them, they just look like visualizations of continuous functions here, even though we know it's actually a list of discrete points. Yowza, that looks professional. I agree. I'm biased, but. Okay, we can also make subplots with Python. I'll show you this just very quickly. I'm not even going to read this code cell. I'll just run the plot. So here are those two functions that we plotted before. They're now graphed separately, but on two different sets of axes that have some things in common. So they're shown side by side. This is again, takes a long time to be able to do in like a Microsoft Excel. This is baked into the functionality of matplotlib. So you create subplots, and then you just use the same plot code within each of the subplots. If you're interested in subplots, you can read up more on those. It's a capability. All right, you may know that in the sciences, anytime we make a measurement, there is an uncertainty associated with that measurement. We never measure anything perfectly. There's always some uncertainty or precision associated with our measurement device. In order to convey that in a data visualization, we usually include error bars. So if I measure the position of an object that's undergoing free fall at some instant in time, it might be 2.3 meters plus or minus 0.1 meters, where that plus or minus 0.1 meters conveys the precision of or uncertainty in my position measurement. The way we display that on a graph is by having a point, that's the value that we measured, and then error bars that kind of radiate out from that point, displaying the uncertainty. Error bars are really tough to do in graphical plotting programs, Microsoft Excel, Logger Pro, something like that, but they're pretty easy to do in matplotlib. So I have a different parabola file here. This one is parab tny underscore error, meaning that it also includes error bar information. And you can check out that data file, take a look at it, download it, play with it. The code for reading in that data file is very similar. I'm grabbing the t value, appending it to a list. I'm grabbing the t error, so the error in the time value, and appending it to a list. I'm grabbing the y value and appending it to a list. I'm grabbing the y error, the uncertainty in the y value, and appending it to a list. I'm converting all of those Python lists into NumPy arrays. And then I use the pyplot error bar plot function in order to make that thing. I specify the t value on the horizontal axis, the y value on the vertical axis, and then I specify that I want the x error, or the horizontal axis error bars, to be the et error, and the y error, the vertical axis error bars, to be the ey error NumPy arrays that I've had before. When I run this thing, whoops, what has happened? Oh man, I gotta get that file too. I'm so sorry. All right, so let's grab this thing, upload, param. I hope I have it. Hey, there it is. Great. All right, so that's uploaded. All right, let's run this. There they are. So here we've graphed, I guess I need to make that a little bit smaller so it'll fit on the screen. There is our error bar graph. Now in this graph, those crosses aren't just, it's like, the shape that I use to display the data point. No, the bars that make up the crosses indicate the uncertainty in the horizontal axis value, which is the time, and the uncertainty in the vertical axis value, which is the y position. So here, maybe closer to ground or whatever, the uncertainty in the y position is smaller. Up here, as the thing gets higher, our precision of measurement of y gets worse and the error bars get larger. So again, in science, when we do experimental science, we always have an uncertainty baked into our measurements. If you're making a sophisticated data visualization, that should be displayed. That error, that uncertainty should be displayed with your data. All right, super duper. You can take a look at this on your own. Even though we're kind of restricted to making graphs in 2 dimensions, because we're doing it on a computer screen, 2-dimensional computer screen, we can graph data that has higher dimensionality. Here's an example of doing that. So here we have a 2-dimensional graph. And it's data that lives in a 2-dimensional plane, but there's actually 4 dimensions of information that's visualized here. There's the value that's on the horizontal axis, there's the value that's on the vertical axis, but then each one of these data points has both a size that corresponds to some other dimensionality of the data, so how big the individual circles are maybe tells us some other property of the data. And each of the markers has a different color. So maybe the color of the marker tells us something else about the data. You might have to make this plot a little bit bigger to actually see that. There it is. So you can kind of see some variation in the size of these data markers in this visualization. Okay, there we go. So I'm going to leave these homework problems to you. Now again, you shouldn't be writing a visualization code from scratch. Many of the code cells that I showed you above in this lesson, you could pretty much just copy them, put in different name for the data file that you're reading in, maybe read that data file in a little bit differently, but if you want to make a histogram, there's no new functionality that you need to learn. The histogramming code is very similar to what it was above. So I'll leave you with that. Hope you're enjoying the lesson so far. Hope to see some comments and emails soon. Thanks for your attention. Take care.